October 12th, 2025. In the early hours of the morning, James Webb Space Telescope completed a focused infrared sweep of 3I Atlas as it moved deeper into the inner solar system. What came back was not the kind of noisy, unstable signal usually associated with dusty cometary bodies. It was clean, too clean. The thermal fluctuations across the object's surface remained narrow and controlled, as though its structure were regulating how it interacted with the sun. And most striking of all, the primary jet, an intense, collimated stream pointing directly toward the sun, held a perfect, unwavering line throughout the entire observation sequence. For an ordinary comet, this level of stability simply should not exist. More data added to the unease. Infrared scattering patterns suggested a fine, engineered surface texture, not the rough, chaotic crust typical of ice and rock. Polarization curves matched layered or structured geometry, hinting at materials that interact with light in a controlled way. And beneath the surface signature, spectral readings revealed something even more difficult to dismiss: a disproportionately high nickel to iron ratio, far beyond what's expected in a standard icy fragment travelling from deep space. This isn't random debris, it's behaving as if it were designed. This object isn't new to you. For weeks, its trajectory has raised alarms. Every element of its path has been deliberate. Its alignment with the ecliptic plane, the near-perfect timing with planetary encounters, the directional echo toward the origin point of the 1977 WOW signal. What James Webb has captured doesn't introduce a new anomaly. It connects the threads of everything that came before. It tightens the picture. It makes the idea of coincidence increasingly hard to defend. And now, the clock is ticking. October 29th will not simply be another astronomical milestone. It marks the perihelion moment, the point when 3I Atlas slips behind the sun, out of direct observation and into a period of silence. For mission planners, astronomers, and analysts, that timing isn't just curious. It's a window, a maneuver point, a gap in surveillance that may or may not be accidental. This is where the story changes. When astronomers began analysing the newest infrared and polarization data coming in from James Webb Space Telescope, they weren't expecting a revelation. They were expecting confirmation, a clearer picture of patterns they'd already observed in lower resolution. Instead, what they received forced an immediate reassessment of what 3I Atlas might actually be. The data wasn't messy, fragmented, or ambiguous. It was sharp, consistent, and disturbingly precise for something that was supposed to be an ancient chunk of ice and rock drifting through the solar system. What stood out wasn't a single anomaly. It was how every signal seemed to align, as though the object's structure was not reacting randomly to sunlight and solar wind, but responding in a controlled, deliberate way. The first clue came from the thermal stability readings. Ordinary comets act like fragile sponges under solar radiation. As they approach the sun, their surfaces heat unevenly, producing bursts of vapor and irregular microjets that fluctuate minute to minute. The infrared signature of such a body should look noisy, a patchwork of hot and cold zones scattered across its surface. 3I Atlas did not behave this way. Its surface temperature remained stable across the entire observation window, with fluctuations so narrow they fell within the margin of instrumental error. That is not normal behavior for a volatile-rich object. It's the kind of uniformity you would expect from a material that's either actively regulating heat or has been constructed to handle it. Then came the jet. The signature that first caught attention months ago was now unmistakable. Instead of a wide, diffuse tail that bent away from the sun under pressure, 3I Atlas emitted a single, narrow, perfectly straight beam pointing directly toward the sun. This is critical. A tail pointing away from the sun is natural, but a stable, sun-pointing, collimated jet contradicts the most basic principles of cometary physics. Solar wind should bend it. Rotation should disrupt it. Outgassing irregularities should make it flicker. But the beam didn't bend. It didn't flicker. It behaved like a sustained exhaust under directional control. The shape, velocity distribution, and light scattering profile all indicated something closer to engineered propulsion than to a random natural plume. Spectroscopy deepened the strangeness. Natural comets are dominated by water vapor, with CO2 and trace volatiles playing secondary roles. But 3I Atlas inverted this relationship entirely. It showed overwhelming carbon dioxide outgassing, minimal water vapor, and a series of metallic spectral lines corresponding to nickel and iron concentrations, far higher than expected for any known icy body. That metallic signature wasn't just strong, it was stable, consistent across multiple observations, and synchronized with the jet emission period. In natural systems, those ratios fluctuate as ice evaporates unevenly. Here, they did not. It was as if the composition of the emission was being maintained, regulated like a process rather than a reaction. But perhaps the most unsettling element was hidden in the polarization curve. When light reflects off a rough natural surface, especially one composed of ice, dust and rock, it creates a scattering pattern, with high variability and low coherence. Negative polarization does occur, but at limited angles and with low intensity. 3I Atlas defied those expectations. Its polarization signature was sharply negative across a broad range of phase angles, a pattern typically associated with fine, microstructured surfaces that control how light reflects. Some astronomers compared the data to engineered reflective panels, suggesting layers or coatings designed to produce specific optical effects. This wasn't a chaotic signal, it was deliberate and clean. When mission analysts began compiling all of these findings into one model, the statistical weight became overwhelming. The chance that all these behaviors could emerge from a single, naturally formed object was nearly zero. Random outgassing does not remain perfectly stable. Natural thermal surfaces do not regulate energy evenly across their structure. Chaotic tails do not align with solar vectors like precision instruments. And random polarization curves do not mimic engineered materials. What the James Webb telescope saw wasn't the profile of a frozen, tumbling relic from the outer solar system. It was the profile of something built to endure, to emit, and to remain stable under extreme solar exposure. For months, discussion surrounding 3I Atlas had hovered in a grey zone between scientific anomaly and fringe speculation. The more data came in, the harder it became to keep that speculation contained. In closed briefings, mission planners began referring to engineered stability as a working hypothesis, not because they wanted to, but because the numbers left them no other option. What was once a curious visitor from interstellar space was now being treated like a controlled object, a probe, a vessel, a system that might be doing exactly what it was designed to do. The stakes rise with every kilometre it travels. In just a few weeks, as it nears perihelion, 3I Atlas will pass through the most intense part of its journey. It will either behave like a comet pushed to its limits, or like something that doesn't fear the sun at all. And if its trajectory and emissions remain as stable as they are now, it will be difficult for any serious observer to keep calling it natural. For many, the strangeness of 3I Atlas begins not with its surface or its jet, but with its path. Long before the spectral data revealed anything unsettling, orbital analysts noticed something that didn't fit the usual pattern. Interstellar visitors tend to arrive at random inclinations, cutting across the plane of the solar system at odd angles, their approach dictated by nothing more than the gravitational chaos of deep space. But 3I Atlas doesn't behave like a drifter. Its orbit is locked almost perfectly within the ecliptic plane, the same flat disk on which the planets orbit the Sun. That single fact alone raised eyebrows, but the precision of the alignment made it even harder to ignore. When plotted over time, its inbound trajectory revealed an astonishing level of order. Rather than slicing through the solar system at a steep inclination like Oumuamua, or grazing the outskirts like 2I/Borisov, 3I Atlas settled into a path that mirrors the orbits of the inner planets. That alignment isn't casual. It's the kind of trajectory you'd expect if the object were deliberately inserted into the solar system, along its most stable, most energy-efficient highway. A natural comet could, in theory, do the same, but the probability is infinitesimally small. One researcher compared it to finding a drifting bottle that not only lands on the same street as your house, but rolls up to your doorstep and stops at the welcome mat. This is where the timing compounds the problem. Its orbital window intersects with 3 planetary positions, Mars, Venus and Jupiter, all in rapid sequence, each within tight temporal proximity. On its way toward the Sun, it passed near Mars's orbit just as the red planet entered its observation range. Not weeks early, not months late. Within a precision window of days. Next comes Venus, then Jupiter's gravitational sphere. A random object should not weave through 3 planetary corridors this cleanly, unless we're witnessing a coincidence of cosmic proportions. Statistically, that level of alignment is less likely than winning a global lottery twice in a row. Orbital mechanics experts initially tried to explain the alignment away as the byproduct of trajectory bias. That is, the idea that interstellar objects might be more likely to enter the solar system along certain paths due to gravitational focusing or galactic drift patterns. But when simulations were run, 3I Atlas didn't match those distributions either. Its approach angle was too shallow, its velocity vector too clean, and its perihelion timing too deliberate. Natural bodies tend to tumble into gravitational wells, slingshot unpredictably, and scatter over time. This one is threading a needle with surgical accuracy. But the story deepens when its velocity is analysed. Most interstellar visitors either accelerate erratically under sublimation pressure or lose velocity after solar encounters. 3I Atlas, by contrast, maintains a speed profile so consistent it resembles controlled propulsion or intentional course correction. No significant velocity drift, no random deviations, no torque from uneven mass shedding. Its course looks maintained, not inherited. There's also a directional echo few expected. Its inbound vector points to a patch of sky remarkably close to the 1977 WOW signal source region. The alignment isn't exact, nothing in space ever is, but it falls within single-digit degrees. For a purely natural object, this could be a coincidence. For one already displaying engineered-like signatures, it adds weight to a growing pattern that's becoming impossible to dismiss. Some astronomers have quietly suggested this trajectory wasn't chosen at random. It was aimed. The implications of a deliberate trajectory aren't small. If an object were designed to maximize its observation avoidance, entering the solar system through the ecliptic plane is one of the most efficient strategies. Planetary bodies and solar interference create natural blind spots for telescopes, making certain approach angles more difficult to track. And if it wanted to remain undetected until it was already deep inside the solar system, this path would have been one of the most efficient options available. It minimizes detection range and maximizes gravitational leverage, like slipping through a narrow door just before it closes. As the perihelion approaches, analysts are watching not just the path itself, but how that path evolves under solar stress. Natural objects wobble as they heat up. They shed mass unpredictably. Their trajectories shift subtly under asymmetric outgassing forces. If 3I Atlas continues to hold its line through increasing solar pressure, the trajectory alone will speak volumes. In some ways, it already does. The mathematics of its path don't suggest chance, they suggest choice. This has created a quiet split in the scientific community. One group maintains that even improbable events can happen, that the universe has no obligation to produce only likely outcomes. The other group sees the stack of improbabilities mounting: trajectory alignment, perihelion timing, spectral signatures, thermal regulation, and calls it what it looks like: a controlled insertion. One astronomer, speaking off record, described it bluntly: "If this were a spacecraft, this is exactly how you'd fly it in." And then there's the timing. October 29th isn't just when the object rounds the sun, it's when it enters an observation shadow. For weeks, astronomers will lose direct line-of-sight tracking due to solar interference. If any maneuver were ever going to happen, it would happen then. This is what has made orbital dynamics teams uneasy. It isn't simply what 3I Atlas is doing now, it's what its trajectory sets it up to do next. The path is locked, the timing is precise, and the window is closing. If the trajectory of 3I Atlas raised suspicion, it was the jet that pushed the conversation from improbable to nearly impossible. Every comet that has ever been studied closely behaves like a chaotic engine. As sunlight strikes the volatile-rich surface, ice sublimates unevenly, creating plumes of gas and dust that burst and bend under solar wind. These jets flicker, fragment, and change direction in unpredictable ways. But what astronomers are now observing with 3I Atlas is the direct inversion of that behavior. Instead of chaos, there is precision. Instead of dispersion, there is control. Instead of a wide, dusty plume trailing away from the sun, there is a narrow, unwavering, sun-pointing column, the kind of stability that, under known physics, should not exist in a natural object. Infrared imaging and visible light scattering models reveal that the jet remains locked to a single axis. Observations spanning weeks show no meaningful drift in its orientation. Even more unsettling is its shape, a tightly collimated beam, narrow at its base, maintaining its structure as it extends thousands of kilometers into space. Natural cometary jets disperse rapidly due to turbulence, solar wind pressure, and rotation-induced wobble. But this plume does not widen significantly. Its profile resembles a controlled exhaust, as if material is being vented in a focused stream, stabilized by internal structure or active regulation. A body spinning irregularly should produce flickering patterns in its tail. None are present. The composition of the jet compounds the problem. Typical comet tails are dominated by water vapor and dust, with minor components of CO2 and other trace volatiles. Spectroscopy from both James Webb Space Telescope and ground-based instruments indicates the opposite here. An overwhelming dominance of CO2, virtually no water signature, and a persistent elevated nickel-to-iron ratio that remains constant over time. Natural bodies shed mass irregularly, composition fluctuates. 3I Atlas maintains a stable chemical fingerprint. It's as though the source material is being metered, controlled, or generated according to an underlying mechanism. The orientation of the jet is just as telling as its makeup. Normally, outgassing occurs on the sunlit side, pushing material away from the sun and producing a tail that points outward. But in this case, the plume points inward, directly at the sun itself. Solar wind and radiation pressure should fight against such a configuration, forcing it to bend and fan outward. Yet the stream remains straight. This implies the jet has enough force to resist those pressures, holding its vector with a consistency that natural sublimation can't match. Engineers watching the data compared it to a controlled thruster overcoming external forces, not to a dusty tail being pushed by them. Polarimetric analysis offers another piece of the puzzle. The way light scatters through the plume tells us about the size and distribution of its particles. A normal comet tail shows a wide variety of particle sizes, with scattering patterns that shift rapidly. 3I Atlas's plume, by contrast, is dominated by particles within a narrow micron range, producing a signature far too clean for a naturally shedding surface. One planetary scientist described it as more like an exhaust vent than a plume of evaporating ice. The jet's persistence also raises energy questions. A natural comet exhausts its volatiles over time, plumes weaken as the material depletes. But this object has shown no sign of weakening, even as its approach toward the sun accelerates. In fact, the intensity of the plume has remained proportionally stable, scaling linearly with increased solar flux. It's as if the system is designed to respond dynamically to environmental changes, maintaining output under stress. No known natural body behaves this way. Some researchers have floated theoretical natural explanations. Perhaps 3I Atlas possesses a particularly stable fracture network that vents gas in a consistent direction, or perhaps its rotation period happens to synchronize perfectly with solar wind pressure. But when those models are run, they require an implausibly exact set of parameters. The fracture would need to remain unaltered despite rising thermal stress. The rotation would need to hold perfect synchronization over weeks. The particle size distribution would need to remain locked. It's theoretically possible, but only in the same way it's theoretically possible for a coin to land on its edge 1,000 times in a row. This is why the jet has become the focal point of most closed-door technical briefings. If the trajectory suggested intent, the jet suggests capability. A natural object cannot sustain such a precise sun-pointing exhaust without either active regulation or design. The plume behaves less like the chaotic exhalation of a drifting rock, and more like a stabilizing thruster, a controlled system, ensuring that the object maintains its trajectory through the inner solar system with surgical accuracy. It's no coincidence that orbital stability and plume behavior reinforce each other. The jet provides a stabilizing force that could, in theory, explain the unnaturally clean trajectory without requiring conventional propulsion. It's a form of vector control, subtle, constant, invisible to the naked eye but decisive over long distances. For mission planners, that possibility is deeply unsettling. It means the object may not only be stable, but maneuverable. And as the object draws closer to perihelion, this jet will either break down under the sun's growing intensity, or reveal that it's something far more advanced than an icy relic. The jet isn't the only feature that's rewriting the rulebook. If anything, it's the thermal behavior of 3I Atlas that may be the most difficult to explain away. In the classical model of cometary activity, temperature is chaos. As a body approaches the sun, its surface heats unevenly depending on its composition, structure, and orientation. Ices sublimate erratically, volatile pockets burst unpredictably, and thermal gradients fluctuate wildly across the surface. Every observation of a natural comet reflects this disorder. But when thermal sensors locked onto 3I Atlas, they found something else entirely. A thermal environment so consistent and finely balanced that it resembled a system under control, not a lump of frozen rock succumbing to sunlight. The temperature profile didn't just remain stable for a few hours, it held steady across multiple observation cycles, even as the intensity of solar radiation increased dramatically with decreasing heliocentric distance. Typically, this would create hotspots, cracks, and plume eruptions as fresh ice layers are exposed. Here, none of that was observed. Instead, the surface warmed gradually and uniformly, with only minimal fluctuations that fell well within instrumental noise levels. That kind of precision is not just rare. It borders on physically impossible for a natural, unshielded object in such a volatile region of space. Infrared mapping of the surface revealed something else. 3I Atlas seems to reflect and re-radiate energy in a controlled pattern. Instead of absorbing sunlight in a jagged patchwork and re-emitting it chaotically, its thermal emission curve looks smooth, as though the entire surface layer is acting in unison. Comets are usually riddled with irregularities, porous layers, fractures, and asymmetries that lead to wildly different heating zones. 3I Atlas, by contrast, displays the kind of uniform thermal behavior one would associate with either a deliberately engineered heat dissipation system or a surface made of materials with unusually high thermal conductivity and structural integrity. And then there's the most puzzling aspect, the absence of expected secondary activity. As comets warm, sublimation accelerates, leading to uneven thrust forces, unpredictable changes in spin, and sometimes violent breakup events. That hasn't happened here. Despite rapidly intensifying solar energy, there's no detectable acceleration caused by random outgassing, no shifts in rotational behavior, no new jet formations. Everything remains locked into the same stable configuration it had weeks earlier. It is as if the object is rejecting entropy. Material analysis only sharpens the mystery. Spectral readings indicate a CO2-rich, water-poor composition, already an anomaly, but also reveal thermal inertia values far exceeding those of porous ice dust mixtures. This means the surface isn't responding to sunlight like a fragile crust. It's behaving more like a dense, structured layer with the capacity to absorb, distribute, and release energy evenly. In simpler terms, it's behaving like a thermal shield. Even more unsettling, this kind of response doesn't just happen by accident. It requires either extraordinary luck in composition and structure, or, more realistically, deliberate design. Astrophysicists have tested multiple natural explanations. One is that 3I Atlas could be made up of an unusually high concentration of refractory materials, dense minerals capable of withstanding extreme heating without sublimation. Another is that it might possess a unique rotation state, slowly spinning in a way that averages out solar heating across its entire surface. But both explanations collapse under the data. If it were primarily refractory, the CO2 emissions would not be this intense or stable. If it were slowly rotating, thermal readings would still display oscillations over time. Instead, the temperature curve is unnaturally smooth, as if the entire structure is actively regulating its energy balance. The thermal data also intersects uncomfortably with the jet behavior. A sun-pointing plume of that strength, coupled with a perfectly regulated surface temperature, hints at a coordinated system rather than a chaotic one. It's the kind of efficiency seen in controlled thermal exchange systems, where energy absorbed from one side is redistributed or vented in a precise way to maintain balance. A natural object cannot choose where to put its heat, but this one behaves as if it can. This is why some mission analysts have started to use language they avoided just a month ago. Words like thermal regulation, active dissipation, and controlled response are beginning to appear in internal reports. Nobody has publicly declared 3I Atlas to be artificial, but the phrasing has shifted from unusual natural object to unknown mechanism. And in the world of space science, that shift carries weight. Thermal modelling simulations also reveal something that makes many uneasy. If the current pattern holds, 3I Atlas will not experience the catastrophic thermal stress events expected during perihelion. Natural comets often fracture, outburst, or break apart as they approach the sun's intense radiation. But this object may not. Its thermal envelope is stable enough that it could pass perihelion essentially intact. That would mean it's either built from an extraordinarily resilient material or designed to survive exactly this kind of encounter, and that raises a chilling possibility. If the object remains intact while maintaining that plume, it may use perihelion not as a random flyby, but as a maneuver point. If the thermal system is engineered, the heat of the sun isn't a threat, it's an opportunity. The sun may be part of the plan, not the obstacle. If the jet suggested precision and the thermal profile hinted at control, the chemical signature of 3 Atlas makes the idea of natural coincidence even harder to defend. For months, spectroscopy teams have monitored the emission spectrum of the object, focusing on its evolving composition as it moves deeper into the inner solar system. What they've found is unlike any other cometary body on record. Its outgassing spectrum is dominated not only by CO2, but by an unusually strong and consistent nickel-to-iron ratio, a metallurgical fingerprint that has no direct parallel among known natural bodies. To put it plainly, it looks less like the loose blend of dust and ice we expect from a comet, and more like the output of something structured, dense, and possibly engineered. Typical comets contain trace amounts of metals, often locked in silicate or sulfide compounds, which appear intermittently in their emission lines as volatile layers are stripped away. The concentration varies chaotically, rising and falling as different regions of the nucleus are exposed. 3I Atlas doesn't follow this pattern. From the first detection of its plume, its nickel-to-iron ratio has remained remarkably stable, a near flat line when plotted against time. It is as if the venting material isn't being drawn from random internal pockets, but from a uniform reservoir or a deliberately composed structure. That consistency over such a long period of intense solar heating is nearly impossible to explain using standard comet models. What makes this even stranger is the scale of the signal. Nickel and iron are present in concentrations far higher than those typically seen in cometary jets. Natural bodies with high metal content exist, some asteroids for example, but those do not emit dense sun-pointing plumes like this. A metallic-rich structure should be inert, not venting in a tightly regulated column, and conversely, objects that do vent usually have low metal concentrations and high ice content. 3I Atlas somehow exhibits both. It behaves like a volatile-rich emitter, while carrying a metallic fingerprint closer to a dense structured core. This combination is alien to any known natural formation process. Astrophysicists initially considered whether the nickel and iron could be contaminants, particles picked up along the jet's path, or background noise amplified by solar scattering. But as the data accumulated from multiple independent observatories, including James Webb Space Telescope and several high-resolution ground-based telescopes, the signature proved resilient. Different instruments, different observation angles, and different times all produced the same spectral peaks. Whatever is producing that metallic signature is intrinsic to the object itself. This pattern is deeply familiar to materials scientists for one unsettling reason. The nickel-to-iron ratio matches not random cosmic dust, but the kinds of ratios found in engineered alloys. On Earth, high nickel-iron blends are used in aerospace applications because of their strength, thermal resistance, and stability under extreme temperature swings. In nature, metallic ratios vary unpredictably. In engineered systems, they are chosen for stability, and 3I Atlas's signature looks far more like the latter than the former. One hypothesis proposed early on was that this could be a fragment of a metallic asteroid coated in a thin, volatile layer, which would explain both the metals and the outgassing. But this theory quickly crumbled. A metallic asteroid wouldn't produce a clean, focused, sun-pointing jet. It wouldn't maintain a smooth thermal curve, and it certainly wouldn't align itself perfectly with the ecliptic plane while sustaining an engineered-looking trajectory. The metal content here isn't incidental. It's a fundamental part of the object's structure. To complicate things further, the nickel-iron signal is strongest at the base of the jet, precisely where the outgassing originates. This implies the metals are not passive inclusions, but part of the emission itself. The particles are uniform in size within a narrow micron range, suggesting controlled ejection rather than chaotic fragmentation. Natural objects shed material in a wide distribution, from tiny dust grains to large clumps. This one seems to be selecting a single size range and maintaining it over time. That level of consistency has no precedent in the natural cometary catalogue. The implications of this discovery ripple beyond the scientific community. If the object's surface or subsurface structure contains engineered alloys, then we are no longer talking about a frozen relic from interstellar space. We are talking about something constructed, something that may have been designed to withstand and operate near a star. And if it is engineered, then its sun-pointing jet could be more than an anomaly. It could be a deliberate propulsion or stabilization system embedded within a metallic frame. Behind closed doors, materials experts have started referring to 3I Atlas as a metallic composite body, not a comet. That language shift isn't casual. It reflects the growing view that the object's physical makeup isn't the result of random cosmic chemistry. It looks intentional. But this brings us to an even more subtle clue: how the light itself behaves when it hits the surface of this metallic structure. The polarization readings, already difficult to reconcile with a natural body, have now become central to the analysis. The way the object reflects, absorbs, and redirects light carries the kind of complexity that only layered, finely structured surfaces produce. And that leads directly to the next anomaly, one that has forced even the skeptics to admit something about 3I Atlas isn't fitting the script. Light doesn't lie. When it strikes a surface, it carries with it the fingerprints of that interaction: scattering angles, absorption depths, reflective behaviors. For decades, polarization curves have been among the most reliable tools for classifying cometary bodies. Natural comets produce predictable polarization signatures. Rough, irregular surfaces scatter light diffusely, creating modest negative polarization at small phase angles that quickly smooths out as distance or viewing angle changes. But when astronomers pointed polarimetric instruments at 3I Atlas, they didn't get the soft, noisy curves of an icy fragment. They got something sharp, coherent, and persistent. The negative polarization signal was far deeper than expected, extending over an unusually wide range of phase angles. Normally, comets produce a negative polarization dip between 10 degrees and 25 degrees phase angles, after which the curve levels off. 3I Atlas broke that rule entirely. Its negative polarization extended far beyond that range, remaining stable even as its orientation shifted relative to Earth and the Sun. That stability alone is extraordinary. Natural surfaces are irregular, their scattering properties fluctuate as new material is exposed, and the polarization signature drifts with time. This one remained locked in place, as if the surface itself was built to control how it reflects light. The consistency of the signal is one of the most unsettling aspects. Over multiple observation cycles, using different telescopes across different hemispheres, the same polarization depth and shape were recorded. These weren't fleeting anomalies or measurement errors. This was a stable optical behavior, and that stability implies something that natural cometary crusts don't have: fine, uniform structure. Cometary surfaces are like cosmic rubble piles, porous, chaotic, unpredictable. They don't produce this kind of clean polarization signature unless something very unusual is at play. Polarization is particularly sensitive to microstructure, the size, spacing, and arrangement of surface particles. A rough surface made of ice and dust tends to scatter light in random directions, producing shallow, irregular polarization curves. A surface with uniform particle sizes or layered reflective coatings behaves very differently. It produces deep, coherent negative polarization over a broad angle range, exactly like what's being observed here. The only known materials to exhibit such behavior are finely structured composites, such as engineered alloys with microtextured surfaces or layered silicate glass interfaces, and yet, here, this signature is coming not from a laboratory sample, but from an object moving through our solar system. The orientation of the polarization signal adds another dimension to the puzzle. As the object rotates, or more accurately, as it moves along its orbit, the polarization pattern doesn't fluctuate the way it should if the surface were irregular. Instead, it maintains a fixed relationship to the jet axis. This suggests that the reflective structure of the object is not random but organized. It may even be aligned with the jet itself. In other words, the surface isn't just scattering light, it's scattering it in a way that reflects a deeper structural coherence. Some researchers have compared it to solar panel arrays, others to heat dissipation layers or engineered reflective shielding. Skeptics have, of course, offered alternative explanations. One proposal is that the negative polarization could be caused by a layer of ultrafine dust, submicron particles that blanket the surface and produce anomalously deep dips in the polarization curve. But when models are run with realistic dust layers, they produce signals that vary rapidly over time as the layer is disturbed by outgassing. 3I Atlas's polarization doesn't behave that way. It doesn't fluctuate, it doesn't degrade, it holds steady as though it's being maintained. Another explanation was that the polarization pattern might be the result of a unique compositional anomaly, perhaps a layer of highly reflective glassy silicates forming a kind of natural mirror surface. But again, this explanation collapses under scrutiny. Natural reflective silicates don't survive long under direct solar heating without fragmentation or opacity changes. The signal from 3I Atlas has not weakened or shifted in spectral character, as its distance from the Sun has decreased. That means the surface isn't degrading the way a fragile natural layer should. It's behaving as if it's resilient, built to handle solar stress. The stability of the polarization curve also correlates with the earlier findings. The trajectory alignment, the unwavering jet, the smooth thermal regulation, and the nickel-iron spike. If this were the only anomaly, it might be dismissed as some rare but natural quirk. But in combination, it begins to form a picture that looks less like a coincidence and more like a blueprint, a structure with layered surfaces, a reflective system built to manage light and heat in a controlled way, a body moving through the solar system with the precision of a machine. This has led to quiet but serious conversations among optical physicists. Some are now comparing the surface polarization of 3I Atlas to known engineered composites, things used in aerospace heat shielding, stealth coatings, and solar energy systems. Of course, nobody is officially declaring the object artificial. The scientific language remains cautious. But the fact that these comparisons are being made at all is telling. When you study comets for a living and you see a surface behaving more like a spacecraft than a rock, it forces uncomfortable questions to the surface. The deeper problem is what such polarization behavior implies operationally. If this surface is designed to manage light, to absorb, scatter, or reflect it in controlled ways, then it may also play a role in thermal regulation or propulsion. The surface could be an integrated component of a larger system, designed to endure solar proximity, and that leads to a broader, more unnerving question. If this is structure, not stone, who built it, and why is it here? As the polarization data continues to hold firm under mounting solar pressure, more observers are conceding what once seemed unthinkable. This may not just be a comet with odd properties, this may be a structure with a purpose. Every anomaly, when isolated, can be explained away. A strange jet, unlikely but not impossible. Unusual composition, perhaps the product of rare formation conditions. Thermal stability, maybe just a lucky rotation state. But when these features accumulate, one after another, each with its own vanishingly small probability of occurring naturally, something fundamental shifts. What astronomers and mission analysts are now confronting with 3I Atlas is not just a single puzzle piece, but a complete statistical landscape that no longer resembles chance, it resembles intent. The stacking of improbabilities began modestly enough, a trajectory locked perfectly into the ecliptic plane, an alignment with planetary orbits that matched transit windows down to the scale of days, a sun-pointing razor-straight jet that violated cometary behavior but was still, in the early weeks, technically explainable through edge case dynamics. But then the anomalies began to layer, each one multiplying the statistical weight of the last. CO2 dominance without significant water vapor, a stable nickel-to-iron ratio matching engineered alloys, a surface that scatters light with the precision of a microstructured reflector. Each new data point didn't just add strangeness, it shrank the odds of natural origin exponentially. Researchers working in orbital mechanics and statistical astrophysics have quietly begun to calculate those odds. The first probability models treated each anomaly as independent, multiplying their probabilities to arrive at a composite likelihood. The result, a natural explanation, falls into the realm of extreme statistical rarity. We're not talking about 1 in 1,000 or 1 in a million events. We're talking about probabilities so small they approach 1 in 10 to the 20 power, comparable to flipping a fair coin and landing on heads 66 times in a row. In scientific terms, that's not unlikely, That's effectively impossible without some underlying organising mechanism driving the outcome. Even those who argue for purely natural explanations admit the math is becoming unsustainable. A comet would need to form in a highly unusual environment to possess such a nickel-iron signature, migrate through interstellar space without losing its volatile balance, enter the solar system along a trajectory that intersects 3 planetary corridors, align itself to the ecliptic plane within a few degrees, emit a sun-pointing jet without turbulence, regulate its thermal envelope against solar heating, and maintain a finely structured polarization signature across a broad range of viewing angles. For all of that to happen spontaneously is an exercise in stacking cosmic miracles. And in science, when you need that many miracles to make a theory work, you usually abandon the theory. This mounting improbability is why the tone inside briefing rooms has changed so dramatically. In the earliest months of tracking, the language used by agencies and research teams was conservative. Words like unusual, peculiar, and uncharacteristic dominated reports. Now the phrasing is sharper, incompatible with standard models, statistically inconsistent with cometary behaviour, and most telling of all, non-stochastic features. Those words carry weight. They signal that scientists are no longer debating whether the object is anomalous. They're debating how anomalous it really is, and what kind of explanation can still fit the numbers. Statistical modelling teams have also begun running reverse scenarios. If one were to deliberately design an object to enter the inner solar system undetected for as long as possible, pass close to key planetary positions and endure solar perihelion without catastrophic fragmentation, the optimal trajectory would look eerily similar to what 3i Atlas is flying now. A shallow ecliptic approach minimises early detection. Sun-pointing exhaust masks its structure and stabilises its course. High thermal tolerance allows it to survive the intense radiation environment without shedding its mass. A metallic core ensures resilience, while a reflective surface minimises heating. This is not an exact match to any known spacecraft design, but statistically it's far closer to a controlled insertion than to a cometary accident. Of course, skeptics continue to propose natural explanations, as they should. One popular argument is that observational bias may have skewed the probability calculations, that objects like 3i Atlas may be undercounted simply because most of them pass through undetected. But this argument collapses against the scale of the deviation. If these were common, we'd expect at least some record of similar behaviour. In decades of cometary observations with thousands of catalogued bodies, none has behaved this way. None has produced this precise set of signatures. Another argument invokes exotic natural processes. Perhaps this object formed in an environment with metallic dust concentrations orders of magnitude greater than higher than anything near our system. Or perhaps it carries a stable crust of engineered-like material formed naturally through unknown processes. But these explanations don't reduce improbability. They shift it elsewhere, creating more questions than answers. Each natural model ends up requiring its own chain of miracles stacked upon the last. This is why many scientists have quietly started calling this the stacking problem. 1 anomaly invites curiosity, 2 invites skepticism, 7 make the default hypothesis untenable. The numbers don't care about personal comfort or institutional caution. They simply describe how likely something is to occur. And in this case, the odds are screaming in one direction. 3i Atlas is not behaving like a natural object. For mission planners, these statistics are not just academic. If this object is artificial, then its trajectory, jet and thermal behaviour aren't just oddities, they're choices. They imply a purpose, however unclear. And that realisation reframes the coming perihelion not as a passing event, but as a critical moment. If something happens then, a manoeuvre, a signal, a change in behaviour, it won't be random. It will be deliberate. And that brings us to one of the most chilling correlations in this entire story. Its inbound vector's eerie echo of a signal that has haunted SETI research for nearly half a century. For decades, the 1977 WOW signal has been one of the great enigmas of the search for extraterrestrial intelligence. A single, narrowband radio burst recorded from deep space, aligned with no known star system and never repeated. It was brief, clean, and unlike anything else that's ever passed through the radio telescopes of Ohio State University Radio Observatory. For nearly half a century, it has remained a historical curiosity, a ghost in the data. But when analysts traced back the inbound vector of 3i Atlas, they found something that stopped many of them cold. Its approach corridor overlaps within single-digit degrees with the same patch of sky that gave us that mysterious transmission. The alignment isn't perfect, nor should it be after decades of orbital evolution and interstellar drift, but it's close enough to demand attention. The object is approaching from a trajectory that mirrors the right ascension and declination window of the WOW signal with unnerving precision. For most of its inbound journey, its path has remained confined to a narrow corridor of space that SETI researchers have long catalogued as one of the most statistically interesting regions in the northern sky. This isn't the same as proving a connection, but it's the kind of overlap that forces serious people to ask uncomfortable questions. The WOW signal's characteristics have always set it apart. It was narrowband, centered around the hydrogen line, a frequency many SETI protocols regard as a kind of universal hailing channel. It lasted 72 seconds, strong enough to be unmistakable, but then it disappeared without repetition. For years, skeptics argued that it might have been an Earth-based interference, a passing satellite, or a rare natural emission event. But none of those explanations ever fit perfectly. The WOW signal remains unexplained, not proven extraterrestrial, but not debunked either. A riddle suspended in the archive of early radio astronomy. Now, an interstellar object with a highly improbable trajectory is entering our system from that same general direction. Statistically, this is a convergence worth paying attention to. SETI researchers have begun to quietly cross-reference historical records, asking whether this object might have passed near enough to our detection range decades ago to produce or relay such a signal. Some have even considered a more radical possibility, that the WOW signal wasn't a random burst at all, so at a handshake, a distant ping, the first and only sign of something that's arriving only now. The trajectory math alone is compelling. If an object departed from a region near the WOW signal source direction at interstellar speeds, the timeline would place its approach in this era, a coincidence that, while not proof, fits uncomfortably well. Add to this the fact that its course is so finely aligned with the ecliptic plane, maximizing its ability to approach undetected, and the narrative begins to harden. The odds of a random interstellar object with these properties appearing from precisely this region are microscopic. Skeptics have been quick to point out that the WOW signal source remains uncertain. The region it originated from isn't tied to a specific star system, and it spans a broad swath of sky. Statistically, any inbound trajectory from the northern celestial hemisphere could be made to appear close, with generous enough margins. That's true. But what makes this particular overlap so difficult to ignore is the combination of factors: the trajectory, the thermal anomalies, the engineered signatures, and now the historical data point that has never been fully explained. Even more telling is the timing. The WOW signal occurred during a period when no major artificial transmitters were known to be active in that part of the spectrum, and the receiver system in use at the time was unusually well calibrated. The burst came and went with clockwork precision. No fading, no modulation drift, no chaotic noise. Some researchers have quietly admitted that if one wanted to send a message from deep space and have it recognized as not natural, that is exactly how one might do it. Short, clean, and placed on the hydrogen line, the one frequency every advanced civilization would recognize. This is why several CT research groups are now preparing for something they haven't done in decades: a coordinated listening campaign during perihelion. Radio telescopes across the globe will be aimed at the region around 3I Atlas's expected position when it passes behind the Sun and re-emerges. If the object is carrying anything capable of emitting, or if it triggers a signal at that moment, this may be our best chance to detect it. There's a growing suspicion, unspoken in public statements, but clear in the internal briefings. If this object is part of something larger, perihelion might not just be a maneuver point. It might be the rendezvous. Others take a more cautious stance, noting that this overlap could still be nothing more than an extraordinary coincidence. But even they admit that the object's behavior amplifies the significance of what would otherwise be a footnote. A normal comet from the WOW signal direction would have attracted curiosity. This object, with its jet, its polarization signature, its metallic fingerprint, and its surgical trajectory, has become something else entirely. For many scientists involved, this is where the story shifts from physics to history. The idea that a signal we dismissed nearly 50 years ago could have been a harbinger, a distant whisper that something was on its way, would rewrite the foundation of modern SETI. And if the object's arrival is more than coincidence, then this is no longer just a comet story. It's a story about contact. As it approaches the Sun, instruments across the world are preparing to listen. No one knows what, if anything, they'll hear. But for the first time since 1977, the silence of space carries a question that feels very close to being answered. October 29th is not just another date on an orbital chart. For those tracking 3I Atlas, it represents the single most critical phase of its entire journey. The moment it swings behind the Sun, disappearing from direct observation for weeks. This is not just a point of maximum solar interference, it's what mission analysts call an observation blind zone, a period when even the most advanced telescopes on Earth and many in orbit cannot monitor the object in real time. Historically, comets have passed through this region many times before, but none of them had the precision trajectory, the stabilized jet, the engineered polarization curve, or the anomalous composition of this one. The orbital geometry is almost too clean. As 3I Atlas approaches perihelion, its path arcs into the Sun's glare at an angle that maximizes the period of invisibility. Analysts at several space agencies have quietly noted that the trajectory seems to exploit the Sun itself as a shield. During this window, direct observation from ground-based telescopes will be effectively impossible, and even instruments like James Webb, Space Telescope and Solar and Heliospheric Observatory, will face severe limitations. For an object whose behaviour has already suggested deliberate design, this timing raises an obvious question. Was this orbital configuration chosen, or is it the luckiest sequence of coincidences in modern astronomical history? This isn't a brief disappearance. Depending on its precise velocity at perihelion, 3I Atlas will remain occluded behind the Sun for a period ranging between 13 and 21 days. That's nearly 3 weeks during which the object can change course, alter velocity, or execute maneuvers without immediate detection. Even a minimal change in trajectory during this time could be enough to place it on a drastically different outbound path, one that would be nearly impossible to reconstruct accurately from its inbound vector alone. Natural comets don't take advantage of such windows. Probes and spacecraft, however, have been designed to. This period is so strategically significant that several mission planners have referred to it, off the record, as a maneuver corridor. If 3I Atlas were to make any form of adjustment to its trajectory, even something as subtle as a half-degree shift, the Sun's interference would ensure that no telescope could catch it in real time. We would only know once it re-emerges. That fact alone has changed the posture of the scientific community. This is no longer just passive observation, it's active anticipation. To understand why this matters, it's worth examining what makes perihelion so dangerous for natural bodies. Most comets entering this region face catastrophic stress. Solar radiation and tidal forces tear their structure apart. Many fragment. Some disintegrate entirely. The fact that 3I Atlas is expected to survive this passage, based on its thermal resilience and structural signatures, is remarkable enough, but its trajectory through this corridor is equally telling. It will pass through a sector of solar space where gravitational shear is minimized, heat absorption is maximized, and observation angles from Earth are worst. For human spacecraft, this would be an ideal moment to mask a course correction. For a natural body, it's just unprecedented luck. The timing also aligns almost eerily with multiple observation schedules. Mars, Venus and Jupiter all occupy positions that, once the object exits its blind window, place it near multiple potential gravitational assist paths. A small adjustment to its trajectory could sling it outward along a new corridor, potentially one that would make future tracking extremely difficult. Analysts are already running simulations. Depending on the delta V, the object could slingshot toward the outer solar system into deep interstellar space, or, more unnervingly, into a stable orbit somewhere between the planets. Some models even suggest a scenario that would have been dismissed as science fiction a few months ago: a controlled insertion into a solar orbit optimized for low detection probability. Such a maneuver would effectively park the object in a long-term observational blind zone, drifting silently while the world continues to argue over what it is. This would require precision, but every shred of evidence so far points to precision being the one thing 3I Atlas seems to have in abundance. The stakes of this perihelion event are heightened further by communication dynamics. Radio telescopes are preparing for potential signal monitoring during the blackout. Any emission or burst during this time could be masked by solar interference, only to be detected in residual echoes or indirect reflections. agencies are setting up synchronized observation campaigns before and after the blackout, hoping to detect a difference. Any sign of altered speed, trajectory, or behavior. There's another subtle factor here that has caught the attention of analysts: the perihelion distance itself. Many comets approach the Sun at unpredictable, often unstable intervals, but 3i Atlas is cutting through at a distance that maximizes both thermal load and gravitational leverage. The kind of corridor an engineered object might deliberately exploit to adjust its trajectory with minimal fuel or external thrust. If its jet is truly acting like a controlled exhaust, perihelion could give it the boost it needs to alter its path dramatically without leaving a trace. For the first time in modern astronomy, agencies around the world are treating a perihelion event not as a curiosity, but as a potential maneuver point. Real-time orbital reconstruction models are being readied. Tracking arrays are preparing for immediate reacquisition once the Sun's interference lifts, and behind closed doors, some have already acknowledged what many have hesitated to say publicly. If 3i Atlas behaves differently after this blackout, we may no longer be dealing with a scientific mystery. We may be dealing with a presence. The orbital window is narrow, it is precise, and once the object enters it, the solar system will, for the first time since it was detected, lose sight of it completely. For months, scientists and mission planners have been studying 3i Atlas as if it were a strange comet, a body with improbable properties, but still bound by the fundamental chaos of natural celestial mechanics. But the approach of perihelion, combined with everything learned so far, has shifted the conversation behind the scenes. Increasingly, orbital analysts are no longer asking if the object could maneuver, they're asking when and how. And October 29th, hidden behind the Sun, is the moment that every model points to. The entire inbound journey has displayed characteristics that seem optimized for control. Its locked trajectory, its stable sun-pointing exhaust, its unwavering thermal profile, its precise timing. These aren't features of a passive body drifting through gravitational currents. They're features of something actively holding a line. That is exactly what makes perihelion so dangerous and so revealing. If any maneuver is to happen, this is where the physics works most efficiently. At perihelion, the gravitational well is deepest, solar pressure is at its maximum, and even a minuscule change in velocity can produce a dramatic alteration in trajectory. A half-degree correction here could translate to millions of kilometers of displacement once it exits the inner solar system. Engineers understand this principle well. It's how human probes like Parker Solar Probe and Bepi-Colombo use gravity assists and burn windows to perform complex orbital insertions. A perihelion maneuver isn't brute force, it's elegance, a minimal impulse at the moment of maximum leverage. If 3i Atlas is under any form of control, it would need only a whisper of thrust to reshape its destiny. Mission analysts have outlined 3 broad scenarios for what could happen during this blackout period. The first, and least likely, is that nothing happens. The object maintains its trajectory and passes back into visibility without deviation. If this occurs, it will not erase the anomalies already observed, but it will at least give some breathing room to those arguing for natural explanations. The second scenario is a controlled course adjustment. In this case, the jet, which has so far behaved like a finely tuned exhaust system, could increase or redirect its thrust vector just slightly during perihelion. Even a change of a few centimeters per second in velocity could send the object onto a new outbound path, perhaps away from Earth entirely, or toward a region where tracking becomes far more difficult. This kind of maneuver would leave no detectable trace during the blackout. We would only see it once the Sun's interference clears and the trajectory no longer matches the inbound predictions. The third scenario, and the one that unsettles even the most disciplined analysts, is a controlled insertion. Using the Sun's gravitational field, 3i Atlas could execute a precise maneuver that would settle it into a stable orbit. Not a hyperbolic escape back into interstellar space, not a slingshot toward the outer planets, but a silent long-term orbit in the inner solar system. A body like this, with its reflective shielding, thermal resilience, and apparent propulsion capability, could remain undetected for extended periods, slipping through observation windows where our current instruments are blind. It could, in theory, become a permanent fixture, a presence hiding in plain sight. Skeptics argue that all of this still assumes too much intent. A maneuver requires not just propulsion, but control, power, and stability. Natural objects can't do that. But then, Skeptics are also running out of explanations for why this object has behaved as it has so far. Every physical parameter we've recorded — jet alignment, polarization, metallic composition, ecliptic trajectory — aligns more closely with what would be expected from a controlled craft than from a frozen block of primordial debris. If perihelion produces even the slightest deviation, it may no longer be possible to maintain the facade of coincidence. Strategically, perihelion is the perfect moment to move. With observation blind spots on every major telescope array, even space-based instruments like Solar and Heliospheric Observatory can provide only indirect measurements, mostly coronal scattering, background flux, and partial light curves. A maneuver could happen beneath that noise floor, invisible to us. By the time the object re-emerges, it could be travelling along an entirely different course, and if that course leads away from the ecliptic plane or behind planetary interference, reacquiring it may prove difficult or even impossible. This is why several agencies, including both national space programs and independent observatories, have quietly begun preparing for immediate post-perihelion reacquisition campaigns. Arrays will be synchronized, radar sweeps coordinated, and deep space networks placed on alert. If anything changes, the world may not know immediately, but the scientists tracking this will. There's another layer to the maneuver hypothesis that many aren't ready to discuss publicly: the timing. A trajectory correction during perihelion doesn't just offer concealment, it offers maximum energy efficiency. For engineered systems, this is the kind of maneuver window that's chosen, not stumbled into. Human missions to Mercury, solar probes, and deep space slingshots have all exploited similar dynamics. If 3i Atlas is operating on similar principles, and the data increasingly suggests it could be, this would be the most rational, predictable moment to act. Some are cautious, warning against overinterpreting statistical noise, but even they admit, if there is a maneuver, it won't look like a burst of fireworks. It will be subtle, controlled, intentional, a shift so smooth it will only become obvious once the math no longer adds up. And when that happens, the question won't be whether 3i Atlas can maneuver. It will be who, or what, made that decision. The idea that 3i Atlas could be more than a comet was once a fringe whisper in the corners of observatory chat logs, the kind of speculation dismissed before it ever reached a whiteboard. But as the evidence mounted, something shifted. Trajectory precision, jet control, thermal regulation, metallic composition, polarization signatures. Now, with perihelion maneuver scenarios on the table, what was once speculation is quietly solidifying into a working hypothesis. 3i Atlas may not be a passive object. It may be a probe. The term being used internally is reconnaissance platform, not because anyone has proof of its origin or intent, but because that's the only framework that cleanly fits the data without invoking statistical miracles. A body with extraordinary stability, engineered resilience, and potential propulsion capabilities, passing precisely through the inner solar system at a time and angle optimized for minimal detection. These are not the hallmarks of random debris. They're the signature of something gathering information, watching, listening, waiting. The first element supporting this theory is its observational stealth. Every phase of 3i Atlas's journey has seemed designed to minimize detectability. Its shallow ecliptic approach delayed its discovery until it was already deep inside the solar system. Its jet, pointed toward the sun, not away from it, masks its structure behind intense solar glare, making detailed optical imaging nearly impossible. Its thermal control prevents the kind of volatile eruptions that would create bright, chaotic plumes, ensuring it remains faint and stable against the solar background. If someone were designing a reconnaissance object to slip through our planetary neighborhood without triggering alarms, this is precisely how they might do it. The second element is environmental endurance. Most natural comets are fragile. They fracture under heat stress, vent unpredictably, and lose coherence near perihelion. 3i Atlas isn't behaving like that. Its smooth temperature curve and reflective structure suggest not survival in spite of the sun, but operation because of it. If it truly is engineered, the sun isn't its danger zone, it's its shield. Perihelion would then serve as both camouflage and opportunity, a place to hide and a place to act. Then there's the metallic core signature. The nickel-iron ratios don't just suggest density, they suggest design choices that resemble what humanity already uses in its most heat-resistant aerospace materials. It's a composition made to last, to endure intense thermal cycling without structural compromise, and the particle size distribution in the jet, microns wide, uniform, precise, resembles engineered ejection rather than chaotic sublimation. These are not random acts of cosmic geology. Even more telling is the behavioral silence of the object. Probes designed for reconnaissance are built to not draw attention to themselves. They don't announce their presence with signals or energy bursts. They observe silently, using passive collection and strategic positioning. 3I Atlas has emitted nothing that we can detect. No radio, no infrared excess, no electromagnetic beacon of any kind. Its entire behaviour, from its first detection to its looming perihelion, is defined by precision without expression. That silence is not evidence of innocence. In intelligence terms, it's the expected behaviour of something that doesn't want to be found. SETI analysts examining the alignment with the WOW signal are beginning to wonder if that transmission wasn't a random anomaly at all. If this object was already on its way decades ago, the signal might have been a ping, a marker, or even a calibration point. A single, elegant burst designed to be remembered, not repeated. A way of saying we're coming, without ever needing to say it again. This is also why the timing matters so much. If this object is operating on a reconnaissance logic, then perihelion is not an endpoint, it's the pivot. A controlled insertion into solar orbit would allow it to remain undetected for long stretches of time, drifting silently in a position where it could observe Earth and other inner planets indefinitely. No constant communication, no obvious energy signature, just persistent presence, the kind of surveillance that would be nearly impossible to confirm and even harder to deny. Naturally, such a theory carries weight far beyond the scientific community. It reaches into strategy, security, and philosophy. If 3E Atlas is an engineered probe, the question of who built it is eclipsed only by when and why. A civilization capable of dispatching an object of this precision across interstellar space would not be making a reckless entrance. This isn't noise, this is choreography. Skeptics continue to push back. They remind everyone that absence of proof is not proof of design, that silence can also be natural, that coincidences, however small their odds, do occur. And yet, in private, even some of those skeptics have admitted, this object behaves too cleanly. It matches too many engineering signatures. It fits too well into the template of a probe designed to slip through our detection net. If this was something we built, no one would call it a comet. They'd call it an insertion vehicle, and that's what makes the next few weeks so critical. Once 3I Atlas vanishes behind the sun, no one will know what it does. Not until it re-emerges. If it returns on the same vector, the mystery continues. If it does not, everything changes. Not everyone is convinced. Even as the narrative around 3I Atlas tilts closer to engineered intent, a powerful countercurrent of skepticism persists, from planetary scientists, orbital dynamicists, and long-time observers who have spent their careers seeing improbable phenomena eventually explained away. These voices remind the community that extraordinary claims require extraordinary evidence, and that anomalies, no matter how uncanny, are not proof of artificiality. They argue that the human mind has a tendency to see patterns and agency where none exists, and 3I Atlas, they warn, might simply be the most statistically inconvenient natural body we've ever encountered. Their skepticism begins with a simple principle. Improbable does not mean impossible. Throughout the history of astronomy, objects have appeared that didn't fit established models, only to be explained later. The strange light curve of Tabby's star, for example, led some to speculate about alien megastructures before dust and natural variability provided a better explanation. Oumuamua itself inspired debates about extraterrestrial origin, but in the end, most researchers lean toward unusual but natural explanations, even if not fully resolved. Skeptics point out that 3I Atlas may be part of this lineage, an extraordinary natural object that is forcing us to expand our models, not abandon them. The trajectory alignment, they argue, may not require deliberate control. Interstellar objects are rare, but they're not bound to behave like comets from our Oort cloud. Their approach vectors can, by sheer probability, align with the ecliptic plane, especially if they're gravitationally focused as they pass through the Sun's sphere of influence. Some celestial dynamicists suggest that we may be observing a form of trajectory filtering. The objects most likely to be detected are the ones that align favourably with the solar system's geometry. In this view, 3I Atlas isn't a precision flyer. It's a statistical survivor. The sun-pointing jet, skeptics argue, may also have a natural explanation, however improbable. Cometary activity is notoriously chaotic, but the chaos can produce stable features under rare conditions. A deep fracture on the sunward face of a dense core could, theoretically, create a narrow collimated plume. If the rotation axis aligns just right with the solar vector, the plume could persist for weeks with minimal deviation. Unlikely is not the same as impossible, they repeat. And rare events are expected to occur eventually if we observe long enough. Even the metallic composition is being challenged. Some skeptics suggest that 3I Atlas may be a fragment of an interstellar metallic-rich parent body, coated in a thin, volatile layer, something between a comet and an asteroid. If it formed in a protoplanetary disk with different elemental ratios, its nickel-iron content could simply be a reflection of that environment. After all, our own solar system is not chemically representative of the galaxy as a whole. It's entirely plausible, they argue, that this is a rare but natural outlier, a body forged in a region of space with an abnormally high concentration of metals. The polarization puzzle has also been contested. A fine dust layer, produced by slow and consistent outgassing, could mimic the smooth, engineered-like polarization curve we've observed. If the object's jet releases particles of consistent size, that might produce a clean signature without requiring technology. Nature has often produced structures and patterns that mirror human engineering, not because they were built, but because physics favors efficiency. The skeptics also emphasize something critical. No active signal has been detected, no radio beacon, no structured emissions, no modulated patterns of any kind. If this were a probe, especially one advanced enough to traverse interstellar space, why the silence? Why not a detectable trace, a signature, or a signal? Some answer this by invoking the idea of a stealth or reconnaissance platform. Skeptics counter that this is a narrative trap, using the absence of evidence as evidence of design. That, they argue, is the most dangerous kind of confirmation bias. Statistically, they remind their peers, improbable alignments happen. We are a single species observing a single event with limited tools. The probability of this object being artificial must be weighed not against its strangeness alone, but against the immense backdrop of natural cosmic diversity. The universe is vast, it is messy, and it is fully capable of surprising us without involving intention. Still, even among skeptics, the tone has shifted. They no longer deny the anomalies, they acknowledge that 3I Atlas is extraordinary. What they contest is the leap from extraordinary to engineered. In their view, the debate should remain anchored in data, not speculation. A trajectory deviation after perihelion would demand serious attention, yes, but not instant conclusions about alien design. Their warnings are clear. If the world decides too quickly that 3I Atlas is a probe, it risks building a narrative before the facts are in. And narratives are hard to undo. Science, one skeptic wrote in a closed meeting note, isn't about believing the most exciting story. It's about surviving the truth even when it's boring. But they also know that their argument is becoming harder to hold as each layer of improbability stacks on the last. If 3I Atlas re-emerges from perihelion unchanged, they may regain the upper hand. If it does not, the centre of gravity in this debate will shift irrevocably, and when that happens, the conversation will no longer be about whether the object is natural. It will be about what to do next. While the world focuses on what might happen during perihelion, a quieter operation has been unfolding in the background, one that could become the first hard, high-resolution look at 3I Atlas before it vanishes behind the sun. In early October, a coordinated observation campaign was initiated involving several orbiting platforms, including assets in the Martian system. Among them is Mars Reconnaissance Orbiter, equipped with some of the most capable imaging instruments ever sent beyond Earth. For once, the object's path works in humanity's favour. Its inbound corridor brings it within line of sight of Mars-based assets, allowing a brief but critical imaging window. Unlike Earthbound telescopes, which are already struggling with solar glare, Mars sits at an angle that places 3I Atlas against a darker section of the sky during part of its approach. This means the object can be imaged at higher resolution with lower background interference, giving mission analysts a rare opportunity to resolve structure that has, until now, been hidden behind thermal regulation and directional exhaust. For months, most of what we've seen of 3I Atlas has been indirect, spectral lines, polarization curves, trajectory solutions. What Mars's orbiters might capture could finally reveal its physical shape. That opportunity is brief, just a handful of days where geometry and lighting align. In preparation, Mars-based instruments have been recalibrated to prioritize deep sky imaging, diverting bandwidth normally used for surface mapping. High-gain antennas are being readied to relay the data back to Earth as quickly as possible before the object moves beyond their observation arc. If the imaging succeeds, the resulting frames will be unlike anything obtained so far. Not scattered infrared heat signatures, but direct reflectance profiles, contours, edges, shadow gradients. Real structure. Mission planners aren't hiding their expectations. They're hoping to determine whether the object has a defined shape. A natural comet, even a metallic-rich one, would appear irregular and diffuse, with a dust halo obscuring most of its body. A structured craft, on the other hand, would produce crisp edges and reflective patterns inconsistent with rubble piles. Even a few clear silhouettes could be enough to differentiate between a random mass and something with deliberate geometry. And that in turn could decide whether the debate remains theoretical or crosses into something far more concrete. The imaging campaign is also designed to study the jet behavior in high detail. From Earth, the plume appears as a stable sun-pointing feature. From Mars, however, the perspective is different. Observing the plume from an off-axis angle allows scientists to measure its true width, length, and particle distribution. If the beam remains as narrow and sharply defined from this angle as it does from Earth, it will strongly support the hypothesis that it is being actively stabilized. Natural plumes, viewed off-axis, reveal their turbulence. Controlled exhaust does not. Another focus of the campaign is thermal mapping at higher resolution. The orbiter's instruments can detect fine gradients in temperature that Earth-based telescopes can't resolve through solar interference. If the object's surface really is regulating heat the way current data suggests, Mars-based sensors should pick up a uniform thermal skin with minimal hotspots. That would be extraordinary, and would narrow the already thin margin of natural explanations even further. Behind closed doors, there's also talk of something far more sensitive: laser ranging. If orbital assets can bounce signals off the object even briefly, they might detect reflectivity patterns that reveal whether the surface is irregular or engineered. No one expects a clean return, but if they get one, if there's a structured reflective layer, the implications would be immediate. Skeptics, of course, are watching closely. They've staked their arguments on the idea that what looks engineered might simply be the result of limited data and awkward angles. High-resolution imagery from Mars could either validate that position or obliterate it. A shapeless, diffuse halo would bolster the natural object hypothesis. But if sharp edges appear, if something angular, geometric, or symmetrical is seen, the tone of this debate would shift overnight. There's a palpable sense of tension in the mission control rooms. This isn't just another data collection pass. For many of the scientists involved, it feels like the first time humanity may get a clear look at something it has only speculated about in whispers. The timing makes it even more charged. These images will likely be the last direct view of 3I Atlas before it disappears into the perihelion blackout. If a maneuver happens after that, these frames could become historical, the before picture that marks the end of one story and the beginning of another. And if the structure seen isn't natural, it won't just confirm what the trajectory, jet, and polarization have hinted at. It will raise a more profound question. If this object was sent, then someone, somewhere, expected us to see it. If the Mars imaging confirms what the trajectory, jet, composition, and polarization data have already implied, then 3I Atlas will not just be another anomalous celestial object. It will be something unprecedented, the first tangible evidence that our solar system has been entered, not just by random interstellar debris, but potentially by an engineered craft. That realization would ripple far beyond astronomy. It would cross into geopolitics, defense, philosophy, religion, and the collective psychology of a species that has, until now, only speculated about what such a day might look like. For the scientific community, the implications are immediate and profound. If this object demonstrates even minimal control or structured design, it will shatter one of the last remaining assumptions about humanity's isolation. The conversation would shift overnight from whether we are being observed to how long we have been observed and by whom. The trajectory of 3i Atlas isn't a chaotic entry, it's deliberate. That means it didn't just arrive here by chance. It came here with a purpose, and in scientific terms, purpose is everything. The first response would come from the institutions best equipped to handle it: observatories, space agencies, intelligence networks, and governments. Global coordination would become unavoidable. Every major nation would want a seat at the table, not to debate the nature of the object, but to control the flow of information. Some would advocate for transparency, others would argue for containment, citing the potential for panic or strategic misuse. The simple act of acknowledging the object as a probe would become one of the most consequential political decisions in human history. For defense communities, the implications are equally staggering. If 3i Atlas is capable of controlled maneuvering, thermal regulation, and stealthy ingress, it represents a level of technological maturity far beyond what we can currently achieve. And crucially, it has entered our solar system without any detectable broadcast, without high-energy emissions, and without triggering any of the early warning systems designed to catch inbound objects. That would be viewed not as a curiosity, but as a demonstration of capability. Not hostile, perhaps, but undeniably deliberate. Some strategic analysts are already modelling what it would mean if the object remains in the solar system after perihelion. A silent probe in a stable solar orbit would be a fundamentally new factor in space security. It wouldn't have to do anything overt to change the world. Its mere existence would be enough to reshape the geopolitical landscape. States would race to develop missions to reach it, to claim it, or to decipher it. The idea of a neutral, shared scientific mission might collapse under the weight of competition. The psychological impact would be harder to contain. For generations, humanity has debated the question of contact from a safe distance. In theory, in fiction, in speculation. Anomalies like Oumuamua or the WOW signal-fueled conversations but never crossed the line into certainty. 3i Atlas might, and certainty is a threshold humanity has never actually faced. Religions would interpret it through their own lenses. Philosophers would ask whether contact had already happened long ago. Millions would wonder why something so advanced would choose to arrive silently. There's also the uncomfortable possibility that we were never the intended audience. If 3i Atlas is a probe, its quietness may not be about us at all. It may be a system designed to observe planetary systems passively, logging data for an origin point light years away. Or it may be one of many such objects, seeded through multiple star systems like silent recorders, watching civilizations rise and fall. That idea isn't new in speculative science, but until now it has lived entirely in the realm of theory. A single engineered artifact in our solar system would drag it into reality. But the implications cut both ways. Skeptics argue that premature conclusions could trigger global panic, political conflict, or scientific misdirection. If humanity labels this object a probe before its behavior is definitively confirmed, it risks making the most consequential assumption in its history on the basis of incomplete data. That's why several agencies are already drafting contingency communication strategies, deciding how, or whether, to announce any structural findings publicly. The most unnerving part, though, is the silence. If 3i Atlas is a reconnaissance platform, then its behavior suggests a civilization with technological maturity far beyond ours. A species capable of sending something across interstellar distances, silently, precisely, patiently, is not a civilization just learning to explore space. It's one that has been doing it for a long time, and such a civilization would not be waiting for our permission to observe. For many within the scientific community, these implications are not frightening in the cinematic sense. They are sobering. This wouldn't be the beginning of a movie with dramatic landings and bright lights in the sky. It would be something quieter, stranger. The realization that for some unknown length of time there may have been something out there, watching, recording, moving with precision just beyond our sight. And that leads to the most delicate question of all. If the object has been observing us, what happens when it decides we've seen it? The clock is ticking. Every hour brings 3i Atlas closer to the moment it disappears behind the sun, and with it the world's last guaranteed chance to observe it before it enters the blackout corridor. The sense of unease among mission analysts isn't theatrical, it's quiet, concentrated and measured. This is the kind of silence that fills rooms where people know history is moving, not loudly but irreversibly. Perihelion isn't just an orbital event anymore, it's a line in time. Before it, speculation. After it, whatever happens next. Control centres across multiple continents are now synchronised in ways they rarely are. Space agencies, defence networks, radio telescopes and deep space tracking stations are aligning schedules with near military precision. The period immediately preceding the object's solar occlusion has become a kind of global checkpoint. Every sensor that can still collect usable data is being pushed to its limits. Spectrometers, polarimeters, radar arrays, thermal imagers, and Mars-based assets all focused on one silent body slipping toward the Sun. There will be no second pass. Once it's gone, the next opportunity to observe comes only after it emerges, and by then, everything could be different. The narrative inside mission briefings has changed. In the early days, the language was academic, anomalous, peculiar, statistically improbable. Now it's operational. Terms like blackout window, reacquisition risk, delta vector uncertainty, and potential course deviation are spoken in the clipped, flat cadence of people who are no longer debating what might be happening but preparing for what could. Some of these teams have stopped calling it a comet entirely. Internally, it has another name now, the object. The most critical stretch is the final 72 hours before perihelion. During this window, the sun's glare begins to dominate, making direct imaging progressively more difficult. Tracking depends on narrow bands of spectral data and angle-sensitive polarization readings, which will degrade hour by hour. This is when even the smallest irregularities in its path would be detectable. A tiny pre-maneuver adjustment, a subtle change in exhaust pattern, or a sudden shift in its spin state. Several teams are monitoring its jet for precisely this reason. If anything changes before it disappears, it might be the only advance warning the world will ever get. But this countdown isn't only technical, it's human. Inside control rooms, people are not just scientists anymore, they are witnesses. They are aware that every line of data could be something future generations will look back on as the moment everything tilted. Some speak in whispers, others work in silence, but the tension is unmistakable. No one is saying first contact aloud, but no one has to. Governments have begun to quietly harden their communication channels. Sensitive information, especially from orbital assets, is being routed through restricted networks. Several agencies have drafted embargo statements and controlled disclosure plans in case something definitive happens during the blackout. What happens if the object re-emerges on a radically altered trajectory? What happens if it doesn't re-emerge at all? What happens if, for the first time, it transmits? Every scenario is on the table. At the same time, SETI stations are on alert. Instruments tuned to the hydrogen line, the same band where the WOW signal was recorded, are preparing for a continuous listening sweep during the blackout period. Even though direct visual contact will be impossible, radio windows remain partially open. A signal, if it comes, could be faint, buried in the solar noise but not entirely masked. Engineers have already built filtering protocols to strip out solar bursts and isolate anything artificial. It's an unprecedented operation. Not because anyone expects an announcement, but because no one can rule one out. The post-blackout phase looms larger in every discussion. If the object returns exactly where predicted, some of the skepticism will regain ground, at least temporarily. If it doesn't, then this will no longer be an academic debate. It will be a historical event. A change in trajectory, however slight, would confirm that the object isn't just a passenger in our solar system. It would mean someone, or something, made a decision. The silence of 3i Atlas has become its loudest feature. No signal, no flares, no visible mechanical signatures, just a precision that no natural object should possess. And in that silence, humanity is projecting everything. Fear, wonder, skepticism, awe. Some still say it's just a comet with quirks. Others look at the layers of evidence and see something much bigger. But soon, it won't matter what anyone thinks. The data will speak, or the absence of it will. This countdown isn't just about an object swinging around the sun. It's about whether, after thousands of years of wondering if we're alone, we're about to get an answer we're not prepared for. The world won't hear a trumpet blast. There won't be a flash in the sky. There will be a change in a line of numbers, a faint deviation in an orbital path, and everything will change. The blackout begins soon. The last clean telemetry is ticking away. When 3i Atlas finally slips behind the sun, the world will enter a strange kind of quiet. Not the silence of space, but a silence of waiting. An entire planet, connected by data streams and a single mystery, will be holding its breath. For the first time in living memory, humanity will be watching nothing. No visual, no signal, just a gap. A dark corridor of uncertainty. This is the part of the story that can't be observed. It can only be endured. Behind the Sun, 3I Atlas will move through its closest approach, crossing the moment of maximum gravitational leverage. If it is just a comet, it will ride the curve and re-emerge unchanged. An odd but natural wanderer on its way back out of the solar system. If it is something else, this is where its path will diverge. It won't happen with spectacle or sound. It will happen in silence, in the invisible geometry of orbital mechanics. Around the world, mission teams have already prepared for the moment of reacquisition. Arrays have been synchronized. Deep space tracking networks have been aligned. SETI stations are scanning their frequencies with filters tuned to catch a whisper in the noise. The global scientific apparatus has never been this focused on one single object in the sky. For months, data points have built a story that feels too precise to be coincidence. But stories are fragile things. In the end, only the trajectory will decide. The most haunting part is what nobody can predict. If 3I Atlas re-emerges on the same course, the debate will continue, loud and divided, with skeptics and believers each armed with their interpretations. But if the object comes out on a different path, even by the smallest measurable degree, everything changes overnight. A deviation would not be a theory. It would be an action, a decision. It would mean that something crossed the dark corridor and chose a new route. And then comes the next question, where it's going. Some models show potential outbound vectors toward the outer solar system, slipping past Jupiter into deep space. Others suggest an insertion orbit, invisible for months or even years at a time, circling the Sun like a silent observer. A handful of projections, the most unsettling ones, show paths that take it closer to Earth's orbital neighbourhood, not intercepting, but watching. For those tracking it, the moment of reacquisition will not be dramatic. There will be no glowing streak across the sky, no thunderclap, just a line of raw numbers appearing on a screen, a Doppler shift, a deviation angle, a signal lock. And in that moment, the story humanity tells itself about its place in the universe will either hold or fracture. Governments are already rehearsing how to respond if the trajectory shifts. Scientists are bracing themselves for a data war between those who want to publish everything and those who will try to hold it back. Ordinary people may not know right away. But when the story breaks, it will not be through a formal announcement. It will come from a leak, an anomaly report, a sudden flood of data that can't be contained. And if this object is a probe, the most unsettling thought isn't that it's arriving. It's that it may have been here all along, silent, patient, watching us while we argued over what it was. The Sun will hold it for a brief moment, a moment where all we can do is wait. And then, one way or another, it will come back into view. When it does, the world may no longer be the same.